Okay, so yesterday we talked about point continuity. What were the three criteria for continuity at a point? So number one, the function must exist, right? If we're talking about determining whether a function is continuous at a point A, where x equals A, f of A has to be defined. What's the second criterion? Okay, the limit exists, and then finally, they agree. There you go. They're equal to each other. Perfect. Okay. So we were looking at this one, right? And I never really read the question very carefully, did I? Let's read through it here. Determine whether the following function is continuous at A, specifically at -7. Okay, so we know that at -7 the function is undefined, right? So it fails the first test, which means it also fails the third test, but we don't yet know about the second test, right? So we got to take a limit. Okay, we've done stuff like this, right? If I try to evaluate this limit directly, what do I get? At -7. So I'm going to get, let's see here. Well, we should be able to figure this out. Let's see, that's going to give us 4 times 7 times 7 is going to give us 28 times 7. This is 17 times. So it's going to be undefined is what's going to happen, right? We're going to get something that looks like a number over 0, right?
279.
Okay. So what's that tell us?
We gotta like trust it.
Does the limit exist? No, doesn't exist. So it fails to exist for, select all that apply. A, yes or no? No. B?
Yes.
C?
Yes.
D?
Yes.
Yes. You guys got this. Goodness. All right, so moving on. So we can talk about types of discontinuities. We can talk about like a point discontinuity means if there's just one point that's out of place. So here are some examples of point discontinuities. That's a point discontinuity, right? It's discontinuous at one point. Here it's discontinuous at a single point, right? What do you think a jump discontinuity is? The limits don't align, right? Limit from the left and limit from the right are misaligned. And an infinite discontinuity is going to be a vertical asymptote, right? And there could be there could be several different possible things. They could both go the same direction from both sides, or they could diverge and go different directions. If I have an asymptote, it's an infinite discontinuity. Okay, we say that a more important distinction is whether it's removable or non-removable. A removable discontinuity is one that can be repaired by filling in or redefining the function at a single point. So it would be of the point continuity variety, right? Removable discontinuity is a point discontinuity. A removable discontinuity can be repaired by adding or moving a single point, okay? A non-removable discontinuity is one that would require an infinite number of points to be moved. And so that is, for that reason, non-removable, okay? So that's an example of a removable discontinuity. That's a non-removable discontinuity. And that's a non-removable discontinuity. Okay? Make sense? Just vocabulary. But you got to get that stuff straight because the textbook will talk about that a lot. Boy, I'm really hammering that, aren't I? What am I doing here? I don't know. I guess I just put that back up there to see it again. Okay, so let's discuss the continuity of this piecewise function. When I say discuss the continuity, it could be a long, boring conversation to talk about all the places where it is continuous. What are we probably focusing on? Where it's not continuous, right? So the top piece taken by itself, y equals 2x, is there any place where that's discontinuous on its own? No, it's good, right? Just a line. How about the bottom? Maybe, right? So the bottom piece is a polynomial, right? The graphs of polynomials we're going to find are everywhere continuous. Polynomials are super well behaved. There's no vertical asymptotes. They're defined for all reals. So both of those on their own are fine. Where's the potential problem?
Where like, if it's not equal.
Okay, so 2, right? Where we're transitioning between pieces could be the issue. So let's check it out and see. Well, let's see, let's go through the checklist. Is the function, so a is 2 in this case, right? Is the function defined at 2? Thumbs up or down? For sure. What is f of 2? F of 2, is that going to be on the top or bottom? Let's make the top red and the bottom blue. It's pretty light blue.
I really need to see that.
Yeah, it's pretty light. Is it red or blue, 2? It's blue. So f of 2, well, I should have used that one, shouldn't I?
You know what, I would say we could count that as like hot pink, I do not think counts as light red.
Oh no, that's light red.
Pink is light red. I know, like hot pink is like, what is?
Oh, I would agree, but this is, I built that color, and you know what I did to build that color? I picked red, and then I just moved the saturation down. So it is literally light red.
But if you like hot pink, you like darken that, it's just like magenta.
No, I agree. It'd be magenta or something, yeah. It'd be somewhere on that spectrum.
You were on too on Friday, right?
We had an in-depth discussion about, yeah. Okay, so anyway, so this is blue, right? So f of 2 would be 2 squared plus 1, which is 5, okay? So yeah, is it defined? Yes, it is defined. Does the limit exist? How would I know?
Check it from the left and from the
Check it from the left and the right. So the limit of f of x as x approaches 2 from the left would be red, right? What's that give us? 4. The limit of f of x as x approaches 2 from the right, we already know the answer is 5. So the limit does not exist. There you go, right? And what would this have to be? What kind of discontinuity do you think this is? It can be a jump, isn't it? Yep. There it is. It's yeah, well, I mean, if it's an infinite discontinuity if really the second criterion doesn't work, right? Make sense? That's really what tells us, yeah. Okay. How about this one?
I'm gonna say it's not
Continuous, otherwise known as continuous. Okay, where's the only place where it might be discontinuous? At 1, yeah. Okay, so, well, let's check it out. What's f of 1?
Like in my head, it was like it's saying x is not equal 1, but if it equals
Okay, so yeah, so what does that mean? What does that piecewise function mean? F of x equals x squared when? Yeah, for all values of x except 1, right? Okay. So f of 1 is what? Is 2. Okay, what's the limit of f of x as x approaches 1? No.
Oh, wait.
What is it?
1.
It's 1. How come? Yeah. Right. Okay, because for all values of x except 1, This is the function, right? It's x squared. Well, in a limit, we don't get to the point. We're just approaching the point. So in the context of a limit, again, let's make this blue and red. I think that red was on top last time, so let's do that. In the context of a limit, well, I should flip it around. So it matches what I already did. Oh, yeah, that's good. So this will be red. And that's blue. In the context of a limit, would the ant be in the blue or the red part of the domain? In the blue, right? So the limit of f of x as x approaches 1 is the same thing as the limit of x squared as x approaches 1, which is 1. Okay? So the function is defined. The limit exists. What's the only problem? They don't agree. So what kind of a discontinuity is this? Point discontinuity. It's removable, isn't it? We have a single point that's out of place. Okay? So write a piecewise function that makes this function everywhere continuous. Okay, let's call this new function g of x. Where is it not continuous? It's 0, right? Okay. So every place except 0, what's our function going to be defined as? Sine x over x, yeah. Right, but I want it to be continuous. Yeah. Okay, what is... What is it? We know that limit. It's 1, exactly, right? So then what's the one other point I need when x is equal to 0? What do I define its value to be? Now it's continuous. We filled in the hole. Everybody see that? Okay? Yeah. Give me thumbs on that. Does that make sense? How we doing? Right? Remember, this was our original function. It had a hole at the point 0, 1, right? Because the function's undefined at 0. Okay. There'll be a review, yeah. Well, I don't know how massive it is. This is in this class. It's well, we have. Okay, but now we're kind of moving down the continuum here. This is really a college level class. So in a college level class, do you think in college they're going to give you a lot of review assignments? No, probably not. They're not really going to give you review assignments because what's the expectation going to be? You review, yeah. There's your review assignment. Go review. I will give you, yeah, I'll put up probably practice tests and stuff for you just this year, you know, but it's, yeah, I mean, mainly review is just go back and review, right? I'm going to help you organize that a little bit, but yeah. Okay. Compositions of functions. Discuss the continuity of g of f of x, right? And those mean the same thing, right? That's, I like that notation better. G, literally g of f of x. So then you see, well, it's, no, I mean in that context, yeah, I would always just convert that into that. Right, that's easier, that's more intuitive. So if we're going to say, let's color code these again. Let's make F red. And G blue. So what this is really equal to then is G of f of x. Well, if g of x is that, g of a would just be that with a's in it, right? G of the quantity x plus 4 would be that with x plus 4 substituted for x's. g of f of x would be that with f of x's where the x's are, right? Okay, so that would just look like the blue level looks like this. Cube root of something plus 11 divided by something plus 4, and that something is x squared minus 4. Okay, so is f of x continuous at x equals 0? Yeah. It is, right? Okay. Is g of x continuous at 0? Is g of f of x continuous at x equals 0? Ah, okay. You see the moral of the story there? The answer is no. Why? Okay, so that's an important lesson. Now explain to me, what did we just learn?
Just because two functions are both continuous don't mean they're going to be continuous when you shove them together.
When I make a composition of those, right? Because what value, now remember how we deal with functions. Functions are just blind eating machines. We feed them input values and they spit out output values, right? Where is the dumb blind eating machine G getting its input food from? In this case, f of x. The outputs of f are what G sees as its inputs, right? So in order for us to determine if G of f of 0 is equal to 0, there's really two parts to that. I have to input 0 into f. Its outputs become the inputs for G. And the output of f of x gives us f of x gives us an output that G of x can't eat, right? It's not in, it divides by 0, okay? That's pretty complicated, right? An easier way to think about it, people always make compositions very, very difficult, but all I have to do is write out the composition and then just look, and then I just merge the layers and look at that as just one different function, okay? If I merge that, well, what do I end up getting? On the bottom, I end up just getting x squared. On the top, I get the cube root of x squared plus 7, right? I get a new function. Okay, that one's got a different domain. This one has the domain x0 has to be excluded, right? Does that make sense? Okay. So, yeah. I don't think. What would be true about it? I would get, what would happen at 0? Would it? Be an asymptote, wouldn't it? Yeah. Because the top is non-zero, the bottom is 0. Yep. Okay, right. Per our discussion. So what's the moral of the story there? You could think about this in two layers by finding outputs of f to become inputs of G, or you could just simplify the function and make it a new function. Call it h of x. That's that. Okay? All right. Okay, so how do we extend our discussion of continuity from continuity at a point to continuity on an interval? Easy, very easy. Let's start off by looking at continuity on an open interval. So between the points A and B, the endpoints A and B. Then all we have to say is a function is continuous on the open interval, A to B, if it's continuous at every point in the interval. That's it, right? That's how we define continuity on an interval. So what do we know? Well, polynomials, as we mentioned, are continuous on any interval. What about rational functions? Well, rational functions are polynomials divided by polynomials. Polynomials are well behaved, but where could a rational function have problems? Anywhere the bottom is 0. Any zeros of the denominator would have to be excluded from the domain of the rational function, but every place else, it's built from polynomials, and so I should be able to graph it without picking my pen off the board, right? So we would say that rational functions are continuous at every point in their domains. As long as it's in the domain, it's continuous on those intervals, right? Okay, so let's look at a function like this one. State the intervals over which the function is continuous. Well, again, it's going to be continuous everywhere but the places where it's continuous, function's continuous every place except the places where it's, well, okay, but just more general. Okay, you guys are discontinuous, right? It's continuous everywhere except the places where it's discontinuous. So what do we look for? Discontinuities. That's it. And every place else is going to be fine. We just are going to focus on the places where it's not continuous, and all the intervals in between, we're going to be good, right? So on this one right here, where would this function potentially be? What would I have to do to determine where this one's discontinuous? It's a rational function. Zero's at the bottom. So I probably want to factor it, right? So we'd write f of x as, does it do this stuff? Well, maybe not. We have to do it. Okay, so so f of x equals x minus 1 over x times x plus 2. So where would this function be undefined? 0 and negative 2, right? So therefore, where is it going to be continuous? Everywhere except those places. Yeah, that's it. Okay, which looks like that. Okay, everywhere, but I've got to omit those points. Okay, what's an easier way to write that? X does not equal negative 2 or 0. Okay. Determine the point or points at which this function is continuous. Well, again, where is it discontinuous? How many places is this function going to be discontinuous? Yeah, how come? Okay, but secant function, if I graph a secant function, a lower s secant function, right? Not a capital S, not where it's, you guys talked about principal domains and stuff last year, right? I'm sure you did. It's where, you know, where the principal domains are where the function is, has an inverse, where it's 1 to 1. That not ringing a bell? Okay, well, we'll need to probably talk about that a little bit. Yeah, okay. So, we need to probably, well, I mean, not really, not really. But that's, okay, somebody make a note to remind me about this. We got, when it's a convenient time, there's maybe some little trig things we want to just build in. 'Cause that's pretty important going into college to make sure you have the trig that's supporting the calculus, and just we got to review some things. So you're feeling comfortable with all that. So that's worth doing. And I might even throw in, just throw in a couple, you know, just some trig practices too, just to kind of get you thinking about that stuff. Like unit circle, I want to really get you thinking in terms of unit circle. We'll probably review some stuff maybe on trig identities and so there, I mean, we'll build in a little trig section where we go through some things. Okay, but now think about a secant. Yes, where are those, if I looked at a graph of a secant function, what are those going to correspond to if I graph a secant function? But if you think about a secant function, like, what is its basic look? Yeah, it looks like u's that go up and u's that go down, right? And I get just an infinite number of those in sequence. And between each of those are a bunch of vertical asymptotes, right? Okay, well, why do we get vertical asymptotes with secant? Because they get zeros on the bottom. Because secant is defined in terms of our basic trig functions, our base trig functions, as cosine on the bottom, right? 1 over cosine. So I'd probably want to rewrite this as 6 over cosine 8x, right? Okay, now it becomes pretty obvious. Every place where cosine 8x is 0, the function has to be undefined. Okay, so now we have to ask that question. Where is cosine of 8x equal to 0? Because those have to be removed from the domain, right? Okay, well, this is a unit circle question, right? On our unit circle, where is cosine equal to 0? I want you to just be certain of your answer. Think about this. Give you a second. I don't want to rush you. Take a second and think about this. Does cosine represent the x or the y coordinate on the unit circle? The x, because c comes before s, right? X comes before y. So where would the x coordinate be 0? Pi over 2 or 3/2 pi or, right? Okay, it's going to be at those places. Now, you gave me specific values on the first lap of the unit circle. But there are infinite number of laps, right? Yeah, so it's going to be, how would I say that? It's going to be 1 pi over 2, 3 pi over 2, 5 pi over 2, negative 1 pi over 2, negative 3 pi over 2. What's the pattern? Okay, you could do it that way, sure. That's fine, you could do it that way. But what's another way of doing it? Think about all those I just said. 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, negative 1 pi over 2, negative 3 pi over 2. Those are just all odd multiples of pi halves, right? Everybody agree? Okay, so it's going to be all the places where odd multiples of pi halves. Well, how do I say an odd number? If I'm going to define n as any integer, so it's just n is an element of the set of integers, represents all integers. How could I specify an odd integer? So if n is any integer, well, I mean, how could I ensure that I'm getting an even integer? If n is the set of integers. Okay, but how do I say that? I mean, like if n represents, n could be 1, 2, 3, 4, negative 1, negative 2, negative 3. Multiply by 2, right? Multiplying any integer by 2 is going to make it an even integer, right? So 2n would be even, so therefore what would be odd? Say it again. Well, no, 1n could be either 1 or 2 or 3. It could be either one. Well, 3n could be either one. No. Okay, we had a good jump on this. You told me 2n was guaranteed to be even. If 2n is guaranteed to be even, how can I guarantee it to be odd? 2n is guaranteed to be even. Pick an even number like 10. Well, how could I get from 10 to an odd number? Subtract 1 or add 1, right? Yeah. How about if we subtract 1? 2n minus 1 is guaranteed to be odd, isn't it? See the trick? If I double n, where n is any integer, n represents any element of the set of integers, that's guaranteed to be even. So if I subtract 1 from it, well, then the result is guaranteed to be odd, because any even number minus 1 is odd, right? Okay, so then what could I do? I could say, well, the solution is going to be 8x is equal to any odd multiple of pi halves, right? Make sense? Okay, well then all I've got to do now is just solve for x, because I don't want the values of 8x. The cosine is being fed functions of 8x, but we're inputting values of x. So which values of x are going to make the angle 8x an odd multiple of pi? Figure it out, solve for x. Right? That's what the math gods they just gave us the answer, but it's a little bit coded, right? It's when that equals that, so solve it. What's the only step I have here to solve for x? Divide by 8. So x equals 2n minus 1, the quantity 2n minus 1 times pi over 16. That's it. I could simplify that. If I split that up, I'm going to get n over 8 minus 1/16 times pi, so I could even do like that. N pi over 8 minus pi 16, or I can just leave it like that. Okay, makes sense? How many values of x did we just include? Infinite. Because how many elements are there in the set of integers? Because that's what n represents. Infinite. So that represents all integers. Take your pick, right? And what do we get then? So let's see. We're going to have asymptotes at, if n equals 0, I would just get negative pi 16ths. Okay, so let's see. It looks like there's negative pi 8ths, so negative pi 16ths would be in the middle. What do you know? That looks like an asymptote there, doesn't it? Right? I should get another one if n equals 1. I should get pi 8ths minus pi 16ths. Well, that's positive pi 16ths. Well, that looks like there's one right there. I got them all. Okay? If n equals 2, I would get, let's see, that's going to give me 2/8 pi minus 1/16. So that's like 4/16 minus 1/16 is 3/16, right? Oh, what do you know? At 3/16 pi, I get another asymptote. Okay? I just represented all of them. So every place else, this function is continuous. It's discontinuous here, so I should say this. X is not equal to those places. Okay? Make sense? Okay? Give me 1 to 5 on that. Probably not 5, but I bet we're moving sort of in that direction. Well, of course, I'm going to give you a chance to practice that on the homework, where you got to think about that stuff a little bit, because that's how you get it. Is you got to do it, not just watch it. Okay, and then this is the last thing I want to talk about today, and then I feel like I've loaded you up with more than enough to get started on some things. So how could we extend this to continuity over a closed interval, right? We know that a function is continuous on the open interval a to b if it's continuous at every place between a and b, at all values of x between a and b. What about a closed interval? Well, then we just have to somehow include the endpoints, right? So we need to extend our idea of continuity to one-sided continuity. Because if a function is only defined from one direction, if it has an endpoint, then you can only approach it from one direction, right? So therefore, continuity only makes sense from a single direction. So we would say a function is said to be continuous from the right at a if the limit of f of x as x approaches a from the right is equal to the value of the function at that place. Okay, makes sense? So the function would exist and the limit would exist and they would be equal. Give me thumbs on that. Does that make sense? We would say a function is continuous from the left if as x approaches a from the left, that limit is equal to the value of the function at that left endpoint again. Okay? If we combine all that stuff then, we would say that okay, this is just more of what I just, oh, here we go. A function is, I'm going to skip ahead one. That's a lot of words. Let's go there. Yeah, this is what I wanted. So a function would be continuous on the closed interval from a to b if it's continuous on the open interval, right? F of x is continuous on the open interval, and it has one-sided continuity at the endpoints. So it's continuous. It's continuous from the right at A, and it's continuous from the left at B. If all of those conditions are met, then this thing is continuous on the closed interval, right?
So you have to approach the endpoints
From inside, right. You can't approach them from outside because the ant has nowhere to stand, right? The function is only, we're only considering, we don't know if the function is even defined outside of A and B. Okay. So that just means if and only if. So f of x is continuous on the closed interval from a to b, if and only if f of x is continuous on the open interval from a to b, and the limit of the function as x approaches a, the left endpoint from the right, equals f of a, and the limit of f of x as x approaches the right endpoint b from the left is f of b. If and only if is a biconditional statement. What that always means is the arrow goes both ways. So I know that if the function is continuous on the closed interval, it implies all that stuff. If all that stuff is true, it implies continuity on the closed interval. Okay? Whew, that's a lot. Okay? I'll put this assignment up. There is a portion of this assignment that I haven't covered yet called the mean value theorem. I'm going to show you guys, that's what I'll do the video on, but I'm going to give you 2 work days to, when I'm gone, to kind of crank away on this stuff. Okay? Work together. I'll put all the videos up, but this is just an opportunity to just think hard and do lots of good problems.